I'm back. So today I'm going to show you how to solve general area maximization problems with physics where they're usually solved with calculus. Now at first this method may sound extremely weird and unnecessary, but as we move on to more difficult problems which might require multivariable calculus, it becomes an extremely helpful shortcut. So please bear with me as this video will talk about the fundamentals of what you need to know. And we'll illustrate this with a practical problem. Steve wants to cut a rope of constant length into two to create a circle and a square. What is the side of the square compared to the diameter of the circle so that he maximizes the total area? So the perimeter stays the same and we want to find the maximized area. This is a standard problem, but we'll solve it with physics today. So we're going to be building a hypothetical physical apparatus. The square and the circle are now hollow, extremely flexible objects. You can fill these objects with gas and they are able to freely expand and contract based off the pressure inside. But before we do anything, let's build a hollow tube that connects these two objects together so that gas from one object is able to move into the chamber of the other object. Now we're going to start filling up the square with gas. And now because there's a tube, the gas can easily move into the circle. Now, what does gas do? Gas always tries to expand in all directions. This is why when you blow a bubble, it is very spherical because it expands in every direction and it always tries to find the maximum area. So if we just leave this apparatus by itself, leave it in a room, and then look at it after a while, it will eventually reach an equilibrium point where it is at the maximum area possible. But if that does happen, we'll just get a giant circle bubble filled with the gas we put, and that's not exactly helpful. So we have to include another apparatus. We need to include a system which is called a telescoping frame, but in this video and in future videos I'll call it a magic rope, which will serve one purpose and one purpose only, and it is to constrain the shape of the two objects. So this will allow the square to expand and contract indefinitely, but it will make sure that the square is always a square, the circle is always a circle. And it will always make sure that the total perimeter is the same as stated in the question. So it can't just be two extremely big objects like that. The total perimeter has to be the same. Now, two more properties come in mind. One is that in this object, the gas pressure everywhere is the same. And if the pressure is the same, the force that is needed to maintain that pressure and prevent it from expanding further throughout the rope is the same. And that force is what we'll call the tension force. So let's look at one specific object. We draw a horrible square here, filled up with gas. This is a close-up of the left part of the apparatus. And we know that the tension force is the same everywhere. The pressure is the same everywhere. So we'll only look at one direction to make things easier. Let's look at the pressure force that acts towards the left. Now, the gas wants to move to the left, but when this apparatus is in equilibrium, or when the area is maximized, it can't move to the left because it's in equilibrium, so there has to be a force that stops it from going left. And that's what I mean by the tension force. And the tension force, as I said, is the same everywhere. That's going to be T, that's going to be T. and the pressure force acting in the left direction is equal to the pressure inside the box times the side that it acts on. So this side, which we already established as A, and these two forces are the same. T plus T, the tension forces added together, is equal to the pressure force. So we can write 2T equals PA, and for the purposes of our examples, P is going to be always 1. So we can write T equals P times A, which is 1 times A over 2. That is our first equation. Now, let's scroll down and let's focus on the circle on the right. And just to mix things up a bit, we fill it up with gas as always. And let's look at the forces if the gas tries to move in the right direction. So we sum up all the pressure that wants to move in the right direction. And since it's in equilibrium because the area is maximized, we look at the magic rope for a telescoping frame that prevents it from actually moving in that direction, and the tension is always constant. Now, the pressure force is equal to the pressure times the side it acts on, which in this case is the diameter. So, and the diameter, as we recall earlier, is just B. So it's P times B. Now, this looks similar. We sum up all the forces. We have 2T equals PB. P is equal to 1, and we have T equals B over 2. And hey, look, we have a system of equations, and this is extremely easy. I expect everyone to know how to solve this. The tension force is always the same, so we have T equals T, and if that's true, then A over 2 is equal to B over 2. Multiply both sides by 2, and we get A equals B. So, when the area is maximized, this apparatus is in equilibrium, and when it's in equilibrium and all the forces are balanced as shown, the side length A is equal to the diameter B. So to solve the problem, if Steve wants to cut a rope of constant length into 2 to maximize the total area, the side length of the square is equal to the diameter of the circle. Now, this is quite an easy problem, and I'm sure many of you could solve this in a much easier way. But what about this? We have a square, we have a triangle, and we have a pentagon. The total perimeter is always constant. What is the relationship between the sides A, B, and C when the area is at a maximum? We'll tackle this problem next video. So have fun solving this with any method you want.